Right, that's got the computer together. So, very good morning to everybody. So my talk is about trying to do microwaves from home. Quite a few things to think about, quite a lot of them technical ones, but we also realize that life's full of other things to think about, including the neighbours, for instance, here. When you do it, you obviously got dishes of this size, you might think look pretty obtrusive arrangements. But with a bit of care and getting the very best technical performance, you can cope with that. So, key factors to think about. Technical performance is really top of the pile in terms of things to think about. If you go on a hilltop and you're 1,000 feet above sea level, you can cope with like relatively small dishes. You can cope with a system that really isn't absolutely perfect, but basically it'll work. I think people have been testified to that when they did their wideband days. I think they really didn't have that much of a problem in going at the top of Snowdon and then going up to south side of, what's it called, Peter, that place?
Cairnsmore of Fleet.
Yeah, Cairnsmore of Fleet, 200 and something kilometres, 10 milliwatts, and it would just work. Doing it from home is a different kettle of fish, okay? You've really got to make it as good as you can to cope with all the losses that you're accruing, not only from the trees, maybe you don't want to put such large antennas up, etc., etc. Part of this talk really is to focus on practical systems. What can you do? What's the limit? How far can you push things, as it were, to get a reasonable performance? Neighbours we've talked about. Serviceability. If you put it up there, whatever it is, whether it be a tower, a pole, or whatever, what happens when it goes wrong? Or what happens when you want to try something different or a different antenna? How do you get at it? So that's quite a factor to think about, okay? I can't actually remember precisely why I put talkback on there. Oh, yes, of course, general talkback. Part of the microwave mechanism is how do you get that feedback? I mean, more recently you've seen computer techniques like KST coming along, which help you set up the contacts, but certainly when you're on the hilltop, you don't always have KST, and talkback is quite an issue. Not just setting your circuit up to try things with people, because propagation can go up and down, so you might be using the talkback quite a long time, and you need pretty good talkback. As people found out when they went portable, you really can't just go for 1 watt and then expect to work down from North Yorkshire down into the south of France. It doesn't go. The talkback doesn't work. What kind of frequency bands are we looking at? Well, this particular talk, I'm concentrating on these upper ones here, this section here, okay? I mean, we can talk a little bit about 24, and I'm looking at Gordon here, who's done very well from his home station on 24 and things like that, but we won't be spending so much time on that. We're really concentrating on these bands. What kind of antennas can you think about for a home system as well? 23 SEMS, you might think of Yagis. You're all familiar with 2-meter Yagis, 70 SEMS Yagis, and things like that. The same technology is available on 1296. To some degree, you can do the same on 2.3. There are quite reasonable antennas available for that as Yagis, quite practical ones. But you're beginning to think about different sort of antennas. You might think about panel arrays and things like that. I've got some pictures to show you later. You might start to think about corner reflectors and things like that. And then of course, there's grid dishes and things like that at these bands. As you get higher up, you're really wanting to get much better efficiency, like the kind of thing you see with this antenna here. This one's 10G, yes, 10G, looking at it. And that's probably a reasonable sized dish to think about for 10G. I think that's a 90 centimetre, isn't it? Whose is it?
I think it's 70 or 80.
All right. So say again, so I can... So
it might be 80.
80, about 80 centimetres. But it's a typical home dish, isn't it, that you might think about using. Not in its normal configuration, of course. It's on its side. You're more familiar with it in its in the other plane, like that, with the offsets and things like that. Up here, in these bands, you're nearly always thinking about dishes. You simply don't get the gain, you don't get the performance. You really have to think about dishes. You move away from sort of dishes that formed out of grids, so you get low windage, you're starting to go for solid dishes and things like that. And in simple antennas, you can think about horn feeds. Then there are dishes with a center fed. Again, I've got some pictures to show you. Offsets like this one. And some people that have used plane reflectors. By that, they've put the plane reflector at 45 degrees at the top of the tower, put the dish on the ground, and use that as a reflector, just like you would with a mirror mechanism. Quite popular at one stage with the professional world, but not used very much now. I remember that RTE, the broadcaster in Ireland, used the main transmitter feed just like that, and it was about a 250-foot tower, I think. Dish was almost on the ground, and a plane reflector at 250 feet up. But the system worked well to feed their transmitters. What do these... A lot of this talk is to talk about practical things, so I keep going back to pictures to show you the practical things rather than getting to lots of numbers and figures and technology. Typical antennas. This is at the top of my house. This is a 23-element Yagi. There's actually a 77s one, and there's a 2-meter one, combined 2-meter and 70, and a 77s long Yagi as part of that on my house. Nobody really worries about that much. Certainly the neighbours don't complain. They think it's just a TV aerial. So it's not massive. I'm not after the DX that's enormously great distances. I can get down into France and places like that quite easily. So it serves a purpose for me. Here's another sort of Yagi. The conventional posts, like you see here, as reflectors. But this is actually made by a company called Masthead. And it actually uses a slot radiator. It's not a tremendously clear picture, this one here, but you can see there's a slot-fed radiator here and a plane reflector. It's actually, he uses a folded piece of metal like that. But that slot-fed radiator works extremely well. If you're thinking of doing television-type work, it's extremely broadband, and it works a treat. So, interesting. I mean, the Yagi is, for any given similar number of elements, is precisely the same length. It's just got a rather better radiator on it. That one's 23. Allows me, for instance, to put that in my loft. That's actually a picture taken in my loft. And it's my transmitter feed onto the local TV repeater on the Isle of Wight. And I cope with all the losses through the tiles and all the rest of it, but it works a treat. Certainly recommend them. I think they also make them, Giles maybe correct me here for this, they make them for 13 SEMs as well, don't they? So, yes. That's the highest band though, isn't it? Yeah, I don't think it goes above 13. No. Very nice antennas. Simpler antennas, or even antennas that you might use for a dish feed. You can see there a couple of diamond-shaped antennas. Effectively, it's equivalent of two dipoles, I guess, in terms of gain. Quite nice for feeding a dish. Very simple to make, not too difficult to set up at all. I actually used one of those recently, just as it was, when I went down to Bournemouth to work their repeater. So there was, broadly speaking, 23 SEMS type antennas you've just seen there. 2.3, here's a selection of those. I mean, Yagis we've talked about. This is a helix mechanism. It's actually a piece of plastic pipe with tape wound around it, and then a matching section made for it. And I was fiddling around using it on satellite reception for it on 2.3. This is the same picture you saw on 23, but you can make a smaller version of that for 13 SEMS as well. This is an interesting one. Inside it, it's actually a horn. It's a straight circular horn, not a tapered horn like this one here with a launcher inside there. And in front of it, there's a series of discs. Quite long antenna it is. And you adjust the space between here to get maximum forward gain. Rather a peculiar looking antenna. Quite popular at one stage, I think, on 13 SEMS. In America, and more particularly in places like Canada, they were often seen. People were experimenting with different antennas. Reasonably easy to waterproof, and quite a reasonable antenna. 3.4, starting to go up in the band a bit now. Well, the first one you see, the bottom right there, is actually two dipoles. I think that one, came from G3LTF, I think, if I remember rightly. I'm actually using it as a dish feed, although clearly you can use it in its own right. It's only got about 3 dB gain, something like that. but feeds the dish quite nicely. You can see I've used a sandwich box as the waterproofing mechanism, because whenever you do these things, you've always got to think about A, the technology, and B, how do you keep the water out? You don't always forever, but you can always put a drain hole in the bottom to let it out if it gets in, I suppose. This one is a panel, a flat plate array. It's actually a printed array. Do you remember the DBS squarial type antennas that everybody said were going to be the best things in sliced bread when you first started direct satellite broadcasting? Well, this is the same technology, basically. It's a flat plane array, and lots of dipoles, and then phasing sections to connect them all up. Lots of inefficiencies, but in the end, you get about 15 dB D compared to a dipole. So it makes a compact, it's only about this big. I use it quite happily at home for 3.4G. And we'll be using it again very shortly at Cambridge when we have the BATC gathering there, because we're going to put an internet circuit on 3.4 between one of the nearby stations. So, going up in frequency again, high up to 10G. Well, we've talked about these sorts of antennas. Here's one of these antennas in its more conventional form. Obviously, the focal point is here. I mean, it is actually, if you think about it, just part of a complete dish, in the sense that if you imagine the whole dish is going around there, this is just one part of it. So if you imagine the whole dish was like that, the focal point's here somewhere, it's geometry. It doesn't matter what the band is, whatever, it's just geometry. So the focal point stays right where it is. I just brought this along as a baby version to talk about it. This one's actually, I use this one on 24G for it. As we see here, one of the things that's quite convenient is if you want to put, you can see here's the focal point here, there's nothing on it, there's no horn feed on it. But if you did want to put more than one feed on, in the way that we've got here, you could actually mount another one. It's not at precisely the same focal point, but it means you could just pan across, and it'd be a few degrees different from one band to another. But you could have a 10G horn feed, or you could have another band. There becomes a point where if you go too low in frequency, the horn feed starts to block a proportion of the dish, so you start to get inefficiencies due to the blockage on the dish. But a situation like this, where you've got all the equipment right up against the horn feed, there's no feeder losses, so it'll work really quite well. Some other examples of the horn feeds. This is actually a horn feed off my 10G equipment here. It's a rectangular horn, simple horn, but it's actually tailored to suit this sort of dish here, and it works very well when measured on a range, antenna range. I think there's somebody giving a talk on antenna range, isn't it? Today? Is that yourself? Is it? Yes. Yeah. It accounted for itself very well. So homemade horn feed, satellite dish, thrown out, nobody wanted it. Put to good use, makes quite a good, efficient antenna. Lots of other clever feeds around, like this one here, mostly derived from similar sort of satellite technology, circular one. It's actually, they're trying to get performance in both vertical and horizontal, so it's a circular mechanism is called for. Lots of variations on feeds, interesting technology, but you don't really have to get that clever to get started. I noticed this one's a horn that's actually made out of double-sided printed circuit board material, and it'll work very well. Efficiency is probably quite good on it. There's things like this. If you want to run more than one band, rather than have two horn sections on it, you could consider putting what is a little log beam in. There's a log beam for 900 megs to 2.5. You can pass that one around. And here's one from 2.1G to 6G. Why don't we use those, you say? Well, the problem is that getting efficient illumination of the dish at all this wide range of frequencies is really quite tough. Quite nice as a little test antenna, and you certainly could put it onto your system and you get a very wide range of bands to cover. So quite interesting for experiment, but downside to that is it's manufactured on fiberglass board. If you put more than about 5 watts in it, you get wonderful little burnt bits all at the top here. I have one that's actually got a nice sort of circular brown bit. It's looking like toast instead of printed circuit board on it. And needless to say, it just burns the board off and burns the copper off in the end, even with 5 watts at the end of the antenna.
Can I just ask you what the horn, what material that is? Is it impregnated or something?
No, it's aluminium.
Oh, it's aluminium, I thought.
Gunmetal, I think. I mean, to be honest with you, you can pick quite a lot of those up, but they are geared up for sort of 12G normally. They'll work, but really you have to try and optimize things. And there's plenty of articles around to show you how to calculate these things and make them up. You don't have to be a super duper metal work. I mean, this is have a look at this one when you come back. Have a good look at it. It's quite carefully made. There's a little bit of solder on the joints, and if you could measure the loss, there'll be a bit of loss due to that. But the fact that it's come in, okay. You could, the copper coating. It's a copper antenna, if you like. So it's actually going to work quite well. And I suspect, looking at that, that's probably really well illuminated for this size of 80 centimetre dish.
Does the ribbing have any special?
Yes. Basically, like a lot of things in life, if you have sharp edges and transitions, it gets kind of tedious, and radio is in the same situation. If you have very large, I mean, really, we would like to illuminate this antenna perfectly, so all our energy falls on the dish. We don't know whose that is. You can't do that perfectly, so you get some spillage. So one of the techniques you try and do with your horn antenna is there to get the majority of the energy in the center and try and get it about 10 dB down at each edge. And the same thing applies to all these other feeds. So that ribbing actually is a way to try and minimize the spillage off the side and illuminate this. If you just think of it in terms of light, if you want to use that as a reflector for a torch, you don't want the light spilling off the side. You want that to do the reflecting. So it's precisely the same logic. But radio doesn't go in precisely straight lines like light waves do, and you get all these edge effects. Sharp edges are bad news on horn fiends and radio generally at higher frequencies. Higher you go up, worse it gets in terms of frequency. Antennas for 24, I've put it for 47 rather than just to explain the techniques really. Here's a center-fed one. I mean, you're all familiar with these center-fed antennas. This one's a Cassie grade. This particular one is a 47G antenna. Quite tough to make those because the shape of the sub-reflector has to be done very precisely. And I take my hat off to those who've made them themselves. I really do, because I think that's quite a tough thing to do. Ones like this are much easier with offset. You can get very good efficiencies, but you can see that this feed is actually in the path and producing more of a blockage to your incoming signal, so efficiencies might not be that good. Here's an interesting one here, an offset a bit like this one. If you can imagine that in that plane like that. I've actually got the transmitter and the receiver units are actually really right up against the feed point against the horn. No feeder losses, or minuscule feeder losses. So every bit of power that I generate here, I get onto the dish. And it works obviously in reverse for the receiver side. The receiver performance is at its best doing that way. This is a little horn feed, which actually is a dual mode, which is the same technique that we were just discussing. How do I stop the spillage off the side? And there are a number of different ways of doing that. There's quite a clever technique of adjusting the phasing of the little horn. It's sort of like two little horns in one. And when you add up all the maths and everything, it sort of makes it tidier at the edges, and you get better efficiency. We haven't talked much about dual feeds other than that log beam, but here's an interesting one. This is actually on my 24G equipment, and it's a dual feed mechanism. The 24G it comes up this guide here, and it's a waveguide output, and then you can feed a 10G in on coax, and it's got like a little probe going into it. Actually works very well. That one is, which one's that? Who's that, Peter?
W1GHZ.
Yeah, W1GHZ produced that. Very excellent articles on those, and quite a practical. I have to admit, I didn't even make that. I think he actually sold you a little kit, wasn't it?
Yes, he still sells
with this block made for you. You put the beer that on, but everything else is done for you, and then you put your waveguide on. It really is excellent. It works a treat. So once again, somebody's used his professional knowledge to the benefit of amateurs, and we benefit from that kind of knowledge. Station equipment. I'm going to speed up a bit now because I think I'm running over a little bit. What do we need? Obviously antennas. You need a rotator. Mine looks like the seagulls have had a go at mine, but it still works. Obviously, preamp up near the antenna is something you need to do. If you're in the case of the microwave bands, you're converting from a lower band. So transceiver, power amplifier, and of course, you need some, these days, usually 12 volt, lots of it. What kind of systems do we have to think about when we're doing a home system? Well, you saw with those dishes where we put the feed horn right up against the dish. It means all the transmitter power gets to the antenna, all the receive systems, receiver energy gets back into the feed horn, so you get the best receiver performance. But that's not altogether practical at these lower frequencies. So one of the critical issues is if you have a switch that transmits from transmit to receive, you really have to put that as close as you can to the aerial. These are mine at home. I think it only is about 1.5 meters. You'll see how I managed to achieve it before it gets to the switch. A lot of people put these things quite high up, and the preamp will go up there as well. Once you've looked after that, the receive side performance will be generally pretty good. If you have enough gain in here, you can normally compensate for the cable losses coming down. You don't even have to have particularly good cable. Not the case for the transmit feed. Obviously, if this is at the bottom of the mast, you really don't want to lose power coming up the cable, so the very best cable you can put in the system is a key issue. And that gets to be mechanically quite an issue, I think, looking after sizable feeder and getting a rotation mechanism as well. So here's one technique then for a home station. It actually is the one I use at home. Whenever I've moved into a house, I put a Velox window right next to a pole. And I got from Germany one of these tiles that you can take the tile out, put the LED flashing in, and put the pole through it. Upside down funnel to water seal it. And it means, for instance, the rotator can sit inside the loft like this. And this distance is rarely more than a couple of meters to the antenna. So you don't have really too many weatherproofing problems. Even the dish feeds that I go up there are really quite short feeder runs as well. One of the benefits from this is that I just lift the loft hatch, stand on a box, and I can change the antenna. And so, remember this comment I made about serviceability? How do you get to it? Well, it's either a tower and tilt it over and work on the ground, or if you want to do something like this, then it makes it quite practical. Feeders, all my transceivers are up here in a box, so what I do on the ground is a bit immaterial, quite small cables going down, easy to rig. So, what have I got? I met that criteria for very short feeder run, so efficiency will be quite good. In my particular case, extremely easy access for changes. I change techniques and antennas quite often, so fairly easy to do. All my key equipment is actually inside the loft. I get told off for going in the loft too much, but that's another story. Don't worry about that. But you do need this special flashing mechanism that I think is readily available in Europe, because you often see, in France and Germany and places, if the power cable usually comes into the building with a pole that appears to stick out the loft or stick out the tiles on the roof. And if you look there, they're using these same sort of flashing arrangements. So they must be relatively easy to get. Not a common technique in the UK for bringing power into the building. There's a picture of it, look. I'm very fortunate that we live on the south coast and the air quality is absolutely superb, as Giles will testify. Okay, so all this is all lichen, even though the house isn't that old. And all I've done is to take the tile out, you slide this thing in underneath it, you make only the smallest hole in the felting to put the pole through, and then you upside down funnel. Been there for 10, 15 years, don't get any water in at all, even though we do get fair storms. Still got a slight problem, again, managing the feeders. They're all sort of lurking about a bit, but in terms of looking after the neighbours, I don't get too complaints at all. One of the techniques I did for a while on 10G. I mean, these are okay. These types of feed are okay for lower frequencies, but obviously when you go to 10G and you start wanting to run waveguide, it gets a bit more complicated. In fact, what I did was I put some waveguide. I cut a slot in it. This is inside the loft, and the feeder went all the way up the top to the antenna and coupled into the antenna. So I actually had waveguide feed going up. It was only about 2.2 meters long, something like that. So it was quite good, quite efficient system. But then you've still got the problem of this is all rotating on the mast as well. So you have to think about those issues. This is the majority of stations I think who run home systems operate this kind of mechanism. You'll often see a pole with a rotator on the ground or a rotator at the top here. Again, I've chosen to put feeder runs for the lower frequencies because you can tolerate the losses to some degree but still get quite a good system. In the case of the microwave stuff where it became critical, well, basically it's all mounted in a box. Up the top, a bit like this, you see here, and then I mean, this one actually is a power amplifier and preamplifier, but more often than not, people will actually put the whole transceiver, the whole conversion equipment, in the box, and we've got some pictures of that too. This is good. I'll just pass this round. It's a good example of what you've got to do when you're thinking about putting things outside. These plastic boxes have got nice seals upon them. There's never enough space. You really don't want an enormous great box up the top because the wind will blow it or it'll fall down or it's difficult to lift. So there's always a compromise between the amount of space you've got. I'll pass that round. You can see the weather seal here. This really is just looking to show you a typical package. And if you look here, when I would have had to go to the next size box to cope with that bump. So I got a bit ingenious about that on the unit. So box at the top, weather sealed. So I mean, this could be a tower as well for tilting over, but I haven't gone into that sort of thing. I'm assuming you don't have that space. This is the unit you see here. I'm not going to go into it too much detail, but basically this was an power amplifier and preamplifier up the top. So I tolerated the losses, and I made up the losses with an amplifier on the transmit side. The preamplifier was actually connected to a mechanical switch here, which was a waveguide switch, you'll see there. So I got the very best efficiency I could. The preamplifier was waveguide in, coax out, and then that was the switch, the antenna switch. But because I only wanted one feeder, I actually put a second switch in. So if you like, it's going like this between transmit and receive arrangements. And I just put some circulators in to stop me from blowing the preamplifier up if the switching inadvertently went dicky. Right, quickly through some other examples. Here's another package which could go at the top. This one is actually off my dish system. So if you see this system here, then this is performing the same task, except I've put everything in there. I got a DB6NT transverter, I got a power amplifier with a heatsink outside the box. I got the smallest possible boxes to do the changeover. Talk about squeezing it in, my goodness me. It cost a lot of mechanical effort to get it in, but and clearly this is not ideal because I've got other holes in here which you wouldn't normally do if you're putting it outside. That lives mostly on my portable system. It can cope with showers, but it can't really cope with other systems. Right, another latter part of this talk then is just quickly running through some more ideas. What have other people done to cope with this business of keeping the efficiency, keeping them practical? Well, this particular one is G3NNS, and it's actually a dual. Remember I mentioned that you can have two horn feeds? There's actually a 5.7, and there's a 10G. Now, I know Brian's actually watching this down in Andover, so I hope I'm getting it right. I have to be careful what I say. Okay, Brian? Didn't hear it right. Offset like that one on its side means you only need to pan. You don't have to worry about doing tilt as well. Bit of a problem that at times because unless you do these things perfectly, you can get a requirement to tilt. Indeed, when it comes to rain scatter and things like that, there's some advantage in being able to tilt your antenna as well as panning it. So you illuminate the cloud on rain scatter, which I think there's a talk about that later as well. Brian's got a nice big tower. He doesn't mind making big boxes and things like that. And you can see here he's got a feeder run at 3 centimetres to the waveguide. So he's keeping his efficiency up here. The transmitter's all up the stick, so he's not losing anything up there. And this is actually the 5.7, which looks as though it's on a piece of coax as well. Typical home prime focus mechanism. You find some way of weather sealing this joint, hopefully don't raise your losses too much. Quite simple structure, a die-cast box to keep the weather out. I think quite a lot of people have used those on home stations. That's Brian's as well, again, I think. Now, it gets difficult when you start going up to 24G. You really want the very best antennas. This is actually a prime focus dish. And you can see there's the feeder coming through here. A nice, again, one of those boxes again, those plastic boxes to get the weather seal. And he's squeezed everything in there, quite cleverly done. Here's the waveguide changeover switch here, the transmit to receive. That, I believe, is the front end of the receiver. This is the, presumably is the local oscillator and the multiplier. And there's, I think, is the PA on the back there, so he's got a heat sink on it. Quite a powerful, really sensitive system. A lot of the equipment's based upon the modules come from a surplus microwave equipment made by the French, I think it was. Alcatel, I think, were the original. Alcatel, weren't they? Yes, that's right, yes. The French sometimes call them the porcupine. They look like lots of spikes on them, on the original heat sink. So you sometimes call the porcupine system. I've almost missed one last point, and then we'll finish off. You remember that I was talking about the... oh, there it is. I was talking about this business of tilting things as opposed to just panning. One of the problems you've got there is you only need a few degrees, and you really need to do it quite accurately. So how do you deal with that? Well, you could put quite a complicated rotator on. But look, here's an interesting little device. There's a little plastic inclinometer here. It's actually got a sensor in it so that it electronically senses to within 0.1 of a degree the tilting mechanism. I think these were from the discount houses for, I don't know, I think it was about £25, something like that. You can take that out. You can put the sensor on your dish and reset the unit like this, and you can actually see the tilt mechanism to within 0.1 of a degree. So whether it's for satellite or whether it's for terrestrial, some nice little add-on devices that are floating around to make your system quite practical. Right, that's me. Any quick questions, I think, before we start the next talk? Or we can deal with questions maybe at the end, if that's right.
Protection of preamps from static.
Oh.
Any thoughts?
Oh, you remind me of Emily Moore. I used to have to go up Emily Moore quite often, and it's every time when you get a lightning strike at Emily Moore, it was about, they calculated it was about 3,000 amps for 10 milliseconds down the feeder, and everything at the bottom used to get just destroyed. The same thing applies to what you're talking about. How on earth do you protect it? I'm not sure I'm that well qualified, to be honest with you. I mean, there's the difference between the energy that's actually coming down the feeder and then there's the energy that's actually in the power supplies. My own experience is that it's nearly always the power supplies that get caught out. So there are relatively simple semiconductor devices right up against the preamp that you can put in there. Don't know what on earth you do for anything that's... I doubt very much if it's actually...
Use a relay to ground the input or something like that.
It's not fast enough, is it? Really?
I'm thinking when it's in a rest state, you know.
Oh, you mean you can put it into a safety mode?
Yeah.
Oh, yes. Well, of course. Oh, sorry, I was thinking when it was active and it was inadvertent. Sorry, I understand what you're saying. Yes, that's always possible. I mean, you can also get, on coax systems, you can actually get gas-type devices that you put in the line. That's how we solved most of the problems at Emily Moore. We actually put these things on the coax lines so that they would either be one-shot devices and they would go short and you had to change them, but the equipment survived on it. But I think there are some quite sophisticated gas devices which were used originally on radar systems, I think. So they do exist. Don't know what else to suggest. Except, I mean, I just put the power supplies together. I have to admit I haven't lost one up the tower, but I think lots of people have. It's part of it.
How often did you have strikes that led you to have to do...
If it's 1,000 feet, For those who are watching overseas, Emily Moore is one of our local transmitters here in Yorkshire. It's up at about 1,000 feet on the Pennines, and then the tower itself is about another 850 feet. If it was in the clouds, it was discharging all the time, basically. But I mean, you're talking here about the transmit feeders that were 6-inch copper. Well, actually, the outer was aluminium, the middle was copper. But you had 4 of those on the antennas. So you can imagine, even if it was 850 feet of 6-inch copper, I think it was worth about 1.2 ohms or something. But 1.2 ohms at 3,000 amps, well, you can work it out for yourselves. I think it's a few hundred volts between the bottom of the ground and the top. Well, the problem is that we used to have video circuits. It was a receive point as well. So you'd actually have coaxes coming down carrying video. Well, the DA at the bottom of the thing just used to disappear. It was the end of all the semiconductors just used to do. You'd have to go and change the DA. I mean, you made your best efforts, but if you got a really big strike, nothing much you can do about it, really. You're relying upon the fact that this feeder is getting rid of most of it for you. When I lived and worked in the Caribbean, I mean, I would go into some buildings and I would... you'd be discharging to they would bond the electricity grid to the ground of the mast of the TV system, and it would be discharging all the time. And when I'd be sitting there in the transmitter and I'd hear this fizzing noise, and I think, I'm not staying here. I'd lock the door and leave and come back when the storm had gone away. It was pretty dangerous business, really. Without, you know. So, no, all the time discharging if it's up there. I haven't actually seen a big strike, but then nearly always the top of the tower would be above the clouds anyway. So you might see sort of a sudden flash of illumination through the clouds, but you never really saw the actual strike. Well, I didn't anyway. Thank you all very much.